It's my pleasure to welcome an old friend, and actually our own former student before my time. But anyway, she got her degree here, in PhD. I met her. Pardon me?
My master's.
Master's, I see. I met her actually when she went to Illinois, where she got her PhD. And then I kind of followed her. She was more in the planning and data structures, right? Computational geometry. And then she moved into, which many people did at that time, into this protein folding, and which is a very geometrical, beautiful geometrical problem. If you are looking for ideas, think about it. But she also is very unique. I don't know whether unique, but as many women in this field, and we are very few of us, I must say, she's really dedicated herself to promote women, and she relentlessly works. I think I work hard, but I mean, there's no comparison to how hard Nancy works. So she has been recognized for her efforts in promoting women, and which is extremely commendable. But she also has worked relentlessly in promoting the international conferences in robotics, and also promoting women in those robotics conferences. So she hosted recently, I visited her at Texas A&M, right? And she organized actually the whole program committee of women. And of course, I was part of that, but she hosted us, and she put up, in Texas, this fantastic barbecue. I mean, you couldn't believe it. I mean, I never had such a great beef. And of course, so in Texas, that's what you get. She got several awards, Nico Haberman Award from CRA, inaugural LCWIT Harold and Notkin Research Award. Anyway, she's a very highly accomplished lady, and we are very pleased to have her here and proud of her accomplishment. So, congratulations.
Well, thank you, Regina. That was very sweet. Yes, I think the nicest introduction I've ever had. So the mic's working still, right?
Yes.
Yeah.
Recording.
Yeah. Oh, you're recording. Oh, so it shouldn't make anything. We're just recording. Okay. Nobody explained that to me. Okay. So, I didn't check this. So, I hope this talk. How many of you? I'm afraid that the talk might be framed at the wrong audience. How many of you know about sampling-based planning? Okay. Okay. So we will try to. I'll try to still make it interesting to you. This is kind of a more general talk that would be, kind of amenable to people who don't know about sampling-based planning. But let's hope that there'll still be something in here for you. So first off, I just want to give you some examples of a number of different types of problems that we can apply sampling-based planning to that are not robotics problems. So we came, sampling-based planning came from robotics community, but it has a tremendous number of other applications. So I'm going to start off by giving you kind of a tour of some of these. Let's hope this will work. So this problem here, the alpha puzzle problem, is kind of one of the benchmark hard problems of motion planning. So this problem, if you're not familiar with it, it has what's called the narrow passage problem. And that particular configuration there, if you know what that configuration is, then the problem is basically easy to solve. But imagine coming up with an algorithm to identify that configuration by itself. It's just not going to happen. So here's some problems from computer-aided design. These are both problems that came from GE, and they're from their aircraft division. This is an example of 2 parts that they designed, and they knew, obviously, that they would fit together because they designed them in that assembled configuration. But they actually chose not to manufacture this because they weren't sure whether or not it would be possible to put them together. And so that's an example, if they had had a motion planner integrated into their CAD system, that they would have been able to decide that, in fact, it was possible to assemble these 2 parts. This here is part of an aircraft engine, and this part that's circled, which is the same, that green one there, it has some requirement that they need to be able to replace it with some, small level of effort. And so the engineer who was designing this bent these pipes to make space and was imagining that this part would get kind of rotated and pulled out. It turned out that was not needed because, in fact, there's a trajectory where the part could come out like this. So it's another example where if they had had a motion planner integrated into the CAD system, they could have gone with that original design. And you could imagine that there's a lot of other applications in this domain with, besides, this is just where it could influence the design phase, but you can imagine training. So a mechanic could be shown a removable trajectory with some maybe augmented reality situation to show them how to move the part rather than looking at these layers of manuals that they typically see. Here's some problems where, oh geez. All right, so these are basically systems that have very many movable parts. This is the one that has the smallest number of degrees of freedom, but it's actually the hardest because when it's moving, it needs to maintain these 3 chains together. This is, I just wanted to show this, frankly, because it's another one of my applications where we have this approximate convex decomposition, and we used it to fit skeletons to the baby model and the robot model, and then we fit motion capture data from an actual boxer to it. But it still shows how we have these similar skeletons, but they're not identical. They don't even have the same number of degrees of freedom, and we fit the motion to it. And here, this looks tough, but it's a large number of degrees of freedom, but it's not. So this is actually the hardest problem here. Okay. Okay, here's a case where we have many different agents. So this here is kind of a disassembly puzzle. It's all these parts that are together, and they need to be disassembled. It's inspired from the assembly problems. Down here we have 2 groups of agents. One is a shepherd, and it's trying to herd these ducks who they don't actually know where they want to go. The shepherd wants to get them in there. They want to stay close to each other and avoid the shepherd. Up here we have just a set of agents that need to traverse this narrow passage. You can see this underlying roadmap which we use. And up here we have a scenario that's from the Texas A&M campus. This is modeled after a building, but we have people that are exiting the building, assembling at their vehicles in the parking lot, coming up with groups together at their cars, and then exiting. And these are basically coordinated motion for many agents. And each one of these agents has its own degrees of freedom, and so we can have arbitrarily hard or number of degrees of freedoms for these problems. And as I'll describe to you later, we use the same underlying framework that we use to solve all these other problems to solve these problems too with multiple agents. Deformable objects. Here we basically have an infinite number of degrees of freedom for the object that we're moving. Here we have basically this teapot and the ducky, the graphics models are following the same trajectory, and they're deforming to avoid collision with that. So they're following the same path. And there's many different ways you could do this, and up here I kind of give you a hint as to how we do that. So finally, another problem that's quite different in nature on the surface, but in fact it's really, we can use the same techniques to solve it, is dealing with molecular motions. And we've been looking at a number of different problems here. Up here we have molecule docking. So here the green molecule, this is two different images of the same thing, the protein and the molecule. And the drug molecule needs to bind into a particular site, the binding site on the protein. Here we have proteins. These are two different types of proteins that are folding into their native state, and RNA folding, which is described a little bit differently. These problems are different from the ones that we were looking at before, because for most of those, we were using things like geometric collision detection to decide whether or not the configuration was valid or not. Here, we're calculating the energy of the molecule to decide whether or not it's feasible. And another difference is that for most of those other problems we were looking at, we were simply looking to find feasible trajectories. Here, we're looking for particular trajectories. And I'll talk a little bit more about that later on when we talk about the protein folding. But all of these problems we've solved with the same planner. Okay? It's really the same code base, and it's the same methods. And as we work on solutions for one of them, we typically learn something which allows us to move it back to the other domain. So for example, on working on the algorithms for the protein folding, we came up with some new ideas that we are now using in the traditional robotics applications. So I won't spend too much time here on the C-space and planning in C-space, but then I'll give you a flavor of a few of the different types of samplers that we've developed in our group, which even if you're familiar with this, you may not be familiar with all those. And then I'll kind of give you a little bit of a flavor about how we apply it to these. So this probably no one here needs, I think, right? Can I go on? Yeah. So the motion planning and configuration space, we transform our simple problem into a simple problem, a one-dimensional point robot, but we have more complicated configuration space obstacles. So just to remind you that solving this problem exactly, we just can't do for any problem of interest. And in fact, today, still the best deterministic method is John Canny's PhD thesis. And so then we use randomized methods, which this leads us to the probabilistic methods. There's two versions of the problem. Basically, we've worked on both versions of it, basically the roadmap-based method and the tree-based methods. This is like the PRM type methods, and the single query will be like the RRT methods. They basically both have the same primitive types of operations that we need. So if you can use your methods for one of them, you can work with the others. So the original method, let me just zip through here, was due to both kind of independently discovered by Lydia Kavaraki and Jean-Claude Latome, her advisor, and Petr Sveska and his advisor, Mark Overmars. And so typically what we all cite is the journal paper. I like to say this because not everyone of your age maybe knows how this came about. But they did this work back in 1996, and this actually, the very first, when I started working in robotics, so I originally did my PhD work in parallel algorithms for computational geometry, and then I wanted to work on something that I thought would be, an interesting area, and I thought, robotics, they probably have hard geometric problems and they need parallel computing. So I went to the library and I pulled out the ICRA proceedings, which at that time were still printed, and it was like 4 volumes like this, so they were like this. And I got really lucky that I found Lydia Kavaraki's PhD thesis paper on the PRM method. And I read that paper, and I'll tell you about actually the idea I had in a minute. But basically it was kind of premised on this idea here. So what was the great thing about PRMs? They are probabilistically complete. So this means, right, if you sample enough, you are eventually going to end up with a roadmap that represents the connectivity of your space. They applied easily to high-dimensional configuration space, which was really revolutionary at the time. We did not have good methods that could solve these high-dimensional problems. And they really are, at some sense, kind of insensitive to the dimension. You simply need to have, you have a point. And if it doesn't matter how many dimensions it's in, you are kind of pushing aside the complexity into your validity check, right? Because that's what's expensive. But you sample a point, and you need to test it for validity, and that can be expensive. And then also those connections. Remember, each one of these connections, how do we test that? We basically look at whatever resolution we care about. We're going to evaluate points on this straight line interpolation between them. So, but they really worked really nicely on a lot of problems that we couldn't solve before. And if you, especially this roadmap-based method, if you spent your time in pre-processing building this nice roadmap, you could then solve pretty much any problem you wanted quickly. So they were really a great breakthrough. But if you think about it, there's some problems that we really care about that they just weren't going to work in that original formulation. And basically, the thing is, it's this whole narrow passage problem. So if you think about it, when you're doing the uniform random sampling, where are you going to get the points? You're going to find the points where the problem's easy, where you actually probably didn't need it, right? But in order to have a roadmap that's going to allow me to move from this position to that position, I need to be able to sample these narrow regions. And uniform sampling is not going to do that. So that's basically the work in my group. We've really pretty much only been working on different versions of this narrow passage problem. And all of those problems I showed you before are some version of that. For example, if you have a task that requires contact, where you need to sample points where the robot's in contact with something, those are points that require you to work on the constraint surfaces. And what's your chance that you're going to get a point like that with a random sample? 0. So that's basically what we've done. And there's lots of different variants that, we've done many in our group, and many others are working on this too. I'd say, pretty much most of the work in sampling-based planning since that original work has been doing, finding some ways to make them be applicable in these types of problems, or in also, the original work was just looking to find any solution. And then there was work on trying to find optimal or shortest paths for these types of methods. So, there's medial axis methods where you want to find points on the medial axis. OBPRM, I'll tell you about that. That's where you're trying to sample near the surfaces. So here was the kind of the idea I had when I read that first paper. It's, gee, we are getting these samples very easily, but they're not where we need them. And they're not getting samples at all where we need them. So can we sample nodes near these C obstacle surfaces when, unfortunately, we can't afford to construct them, right? They're too complicated. On the other hand, we have these models, the workspace obstacles, which we weren't using at all. So here's this basic idea. I don't know how many of you are familiar with this method, but it's really simple, and it works surprisingly well. But the idea is, suppose you have some configuration that's in collision, for, me, my arm through the podium. Then you have another configuration that's free. Now we have this random direction in configuration space. I look for this point out here. And once you're in this situation, you're home free. We can use a bisection search to find a point. Oops, I think I hit the blank screen. Yes. To find a point near the surface, whatever resolution I want. So after I do this, I'm going to continue between 2 and 3. Now between 3 and 4. And let's say I'm happy with this resolution. One of the kind of the dissatisfying, so this turns out to work really well, and it's pretty cheap, and it worked quite well in those problems that the original PRM methods weren't working. I would been dissatisfied with this method for a long time because I wanted to be able to prove something about the distribution of the points I get on that surface. And this illustrates one of the challenges. I have this random direction. I have no idea how many times it's going to intersect the surface. I just know that I find one of them, and I have no idea which one it is. The only way to know for sure would be to basically check every single point, right? And this would be too expensive in general. That was like something that bugged me for a long time. So another method that we came up with was sampling on the medial axis of the free space. This is nice because sometimes you want to have clearance. Okay? Now again, you have the challenge. We can't actually compute the configuration space obstacle surfaces. So how are you going to decide whether or not you have a point on the medial axis? Well, here's how we did it. We sampled a point in the configuration space. If it's in collision, I find the closest boundary point to it. Then I push it in that direction until I get to a point that has more than one that's equidistant from this surface and another surface. And if you selected a point originally that was already in the free space, you do the same thing. You find its closest boundary point, you push away from it, and you stop. The really nice thing about this is it actually is going to increase our probability of sampling in the narrow passages. So here's just two different cases. And let's say that this part of this isn't the narrow region. And my probability of getting a sample in here using this simple uniform sampling is just the volume of this corridor over the volume of the entire C space. Using that strategy I just described to you, any point that I sample in this shaded region is going to end up in that corridor. So the volume, the probability of getting a point in that corridor using that strategy is much higher. I'm going to take the volume of that corridor plus the volume of the surrounding obstacle with this over the volume of the configuration space. So it doesn't always end up helping, but if you have surrounding obstacles that are, let's say, fat, this can help a lot in increasing your chance of sampling in the corridors. And that was, I think, the quite nice thing about this. This would be, usually someone asks me a question at this point.
Okay. How do you know the blue line? The medial axis?
Okay, so there I'm supposed to stop. So let's say this is what I wanted you to ask me. So the challenge is, how do I know, the real question is, how do I know the closest boundary point, right? So when I don't actually have the configuration space surface. It turns out that you can actually you can afford to compute this directly in some very special cases, but nothing, only in these lower dimensional cases for some particular metrics. So we can't really do this in any real problem that we care about. So what we do is we just approximate it. And what we did for this is we will select a few different directions. And we will walk in that direction to find a boundary point. And we just used the closest one. And it turned out, so then the points are not going to be guaranteed to be on that surface. But it turned out to work pretty well. And when we just inspected it, like for two-dimensional cases, it does end up getting us these kind of high clearance points.
Nancy, how does this compare with some peak potential energy? Remember we had
Yes.
Yeah, and it really is very much like the...
It is. So these elastic bands type things, yes. So there's some things that are similar, but some things that aren't. So that would basically take a trajectory and from that kind of push it away by kind of blowing up these balls. So in some sense you could, here we are just trying to get the points. So that was more trajectory based and shifting it there, but it is similar. But it's also, that was very much workspace based, I believe.
Oh, he did that also. That's correct, yeah. He did that in workspace, yes.
But you can do the same thing in configuration space, and in fact, we did do that as well. But it's kind of similar, I think. But this will work kind of in arbitrary dimension too. Yes.
I have a general question regarding TRM.
Uh-huh.
So, like, do we include some notion of visibility of the trajectory that we come up with at the end of the day?
Mm-hmm.
But then if a system can follow that trajectory, do we have any notion for that? Or?
Okay, so well, this is where there's two versions of the problem of these methods, right? The RRT, which is typically what you often may use that can address some of these things. But each one of these sub pieces. Should we go back? Well, let's just go here. Each one of these is a trajectory that's tested with your local planner, right? Each edge. And so each one of them should be, in principle, feasible. And you should be able to connect them together. Now, this is just the simplest version of this that's, I'm showing you in basically configuration space. We can do this like in belief space too, and you can put whatever constraints you wish on your local planner. On the other hand, once you pull out a trajectory, you never expect it to be followed precisely, right? This is just kind of encoding for you some approximate trajectory. Then it's once you need to actually follow it, you would smooth it or apply whatever you needed. This is really identifying for you a region in C space to move through.
So in the narrow passage example, if you were only able to follow the trajectory approximately, how do you know that the deviation is small enough to still fit inside the narrow passage?
Well, that's so when you set the resolution for these methods or when you select your local planner, you should select it so that it satisfies whatever your criteria are. So that will be you need to set up your problem appropriately. So one thing I wanted to show you, so I told you it was bugging me forever to try to get a nice distribution of samples on this surface. So finally, and I wanted to work a little bit more on this slide, but finally we have cracked this nut. So it turns out it's really simple. So before, we were just sampling points, individual points. If I want to cover a surface uniformly, it turns out that if instead of sampling points, if you sample segments, so I have fixed size segments, and you imagine just tossing them into your configuration space. And then you take all the points that you test on that segment, you look for all the intersections for it with the surface, and you keep all those points. It turns out it's pretty easy to show that will actually give you a uniform sampling on the constraint surface, on any surface. So we can use it to sample like the surface of an obstacle. We can also use it to sample the medial axis or any surface you care about. And it was so simple.
So not just like a particular construction, like
We'll ask.
Sorry, I'm getting a little off topic.
So, but no,
I mean, never mind. I'll ask you later. I'll ask you
okay, all right.
I mean, do you assume a certain representation of the target surface, or is it again like sampling
Any surface, that you need to be able to test whether or not you have crossed that surface with a segment. Exactly. Right. Well, you won't do binary search. You're actually going to have to check at every point at whatever resolution you care about on your segment. Because if you just do a binary search, you can't, before I was testing whether or not it was in collision or not, and then I was searching to get close to the surface. Here, I'm going to test, and I'm going to see if I'm crossing the surface between any 2 points. The line segments they're fixed size, but you need to uniformly sample those. But it turns out, this kind of gives us, the thing is though, this is uniform sampling of this, so it's not going to give us those benefits of some of those other ones that were helping us, where we were trying to focus just in the narrow region. But it gives us a nice surface, and it turns out to be, the reason we came up with this, frankly, is because we were trying to look for binding sites for ligands on a protein surface. And this turned out to be a good way, because we wanted to cover the whole protein surface. And this turned out to work well. And then we brought it back into and applied it to some of the other robotics applications. So anyways, that was something that I wanted to solve forever. And here's, yes?
How do you choose the line segments
The
so that they're going to have a high chance of crossing the surface?
Well, that's kind of the black magic there. You need to decide, how long they should be. And there's a trade-off. If I choose a very long line segment, it's going to take me much longer because I'm going to have to check each one, because I have to check at whatever resolution I've decided on the entire line segment. If I dial them down to basically almost a point, then it essentially degenerates into uniform sampling. So there's a trade-off in the cost for each segment that you test as to how many. And if they're long, though, your chance of finding something is pretty high. So here's another one that maybe you didn't hear about yet that I think is kind of interesting. So in the traditional philosophy, we map only the free configuration space. And it's really tough to tell the difference between this problem and this problem. In this problem, there is no passage at all. Okay? How am I going to figure that out? And in this one, there is a narrow passage. So the idea here, and this is work that was done by the very first high schooler that worked with me and one of my PhD students. And he did very well. He won the Siemens national competition for that. It's the only student I ever had where I had Stanford and Harvard were calling me. Stanford, Harvard, and MIT were calling me and trying to get him to convince him to go there for undergrad. So, so here's the idea. What if we also map the blocked space? Okay, so I'm going to make a map of the block configuration space. And over here, I would end up with, these aren't supposed to be here yet, but I would have a connected component here and a connected component here. And I would not have this edge. I wouldn't be able to connect that vertex to that vertex, say, where I did over here, because it will go through this narrow region. So the idea here is I'm going to simultaneously map the free space and the block space, and I'm going to retain witnesses from failed connection attempts and add them to the opposite map. So when I try to connect like this point to this point, it's going to fail. And then I'll have a point in my narrow passage, which I can now add back to this map. And it turned out, it only works in certain cases, but if it does, here's some examples of so here's like 3 different versions of the passage where I made it increasingly narrow. And here's the one with the wide passage down to the narrow one. And the red bars are the number of free nodes I got in the narrow passage using that method. And you see I still get quite a few using this toggle version. And the reason there's fewer is because there actually are going to be fewer because it's narrower, right? But one thing about this is it really kind of, one of the things about probabilistic completeness for these methods is we will say you need to sample and sample and sample. You'll need to sample more if the problem's hard. Using this strategy, that's not true anymore. In fact, you can solve this problem really quickly. Think about back to this problem here. This one would require a lot of samples with the normal method of doing this. But for this one, we'll really quickly end up with points in the narrow passage. And once you have points in the narrow passage, you're home free. You can basically run your RRT method there. So this is usually a point where people ask me something else. Yes?
How do you choose which points to try and connect? Is it like reverse neighborhood?
Oh, yeah, OK. So that's what I skipped over, assuming everyone knew how the PRM method worked. So the way the PRM method works is once you have, the first phase is you sample, and then you try to connect. And when you try to connect, you're going to try to connect a point to its k nearest neighbors, where k is some small constant. usually even just 5. So after I have done all my sampling, I find my 5 nearest neighbors. I try this local planner connection to it, and that should be pretty quick, and you're going to use a deterministic method for that. And that's where we just use normally the straight line interpolation and check all the points in between it. Yes? Okay, so this is the question. It works here because this narrow passage separates these two regions of the block space. So the answer is it works in some cases. Even in 3 dimensions, if that narrow passage is just like a tube, it's not going to work, right? Because all my points around it, when I try to connect them, they're not going to go through that narrow tunnel. On the other hand, if my separating region is like a plane, it'll work. So we came up with this definition of, kind of locally separable. So if a point, if there's some kind of either the free or the block space kind of locally separates the other spaces, this will work. And it only has to be true locally because we're only trying to do these connections locally. And so there are many spaces where it's not true in, but there are also a lot of interesting spaces where it's true. In particular, spaces where you do have contact tasks, this is often the case. Okay. Yeah, I think that was, there's just lots of other variants of this. This is just give you some small set of the ones, and they're all ones developed by my group, of course, but lots of other people have been working on this, and there's many different ways. And I think today, there's still, a lot of problems we can't solve, but we have a lot of different methods for doing this, and many times we put them together. So let's see. How are we coming? Okay. All right. So, yeah, for sure, one thing, let's see, I think I'll tell you about maybe the first and the last. So this is something that I'm really interested in working on, and it's really, so all the motion planning methods we've had before were really kind of just intended to work totally autonomously. You just set up the problem and you start them on it. But when you look at a problem like this, we all know really what the trajectory looks like. It looks, roughly something like this, right? And on the other hand, when we now imagine with these sampling-based planners, you ask it to solve that problem, that's a really tough problem for it to just, sample some of those points on its own. Even with these different methods that we've come up with, it's very difficult. So for this, we were using, we basically wanted to find a way to let the user help out the planner. And so what we did is we would let the user collect kind of an initial rough trajectory we used a phantom haptic device for that. And you can imagine that what you might get is some kind of approximate path. Okay, because it's not going to do precise collision detection, and we'll just kind of roughly sketch out the path. And what this is really doing is it's identifying a region of the configuration space for the planner to search. So you've really reduced the search space now, and you've asked the planner to focus there. And so what we did is we now can look at this approximate path. We identify the valid portions here and the invalid portions. And now we're going to use those invalid portions and try to fix it. And we can apply those methods that, similar to what we've done before, to these obstacle-based methods where we're pushing points out to try to improve that. So that's basically what we would do, is we would try to repair that path. You mean to sample on the medial axis in the high dimensions?
Well, whatever you need to do in order to get the
Well, computing the medial axis in that high-dimensional space is just expensive because you need to have, appropriate, distance metrics.
Is it time-consuming or memory expensive, or what is?
Often it's that we don't even really know how to define it, right? How to define it. So what's the appropriate metric for that? Now, what we're doing, this approximate sampling on the medial axis, works pretty efficiently and often is, I think, good enough. Now, that's just sampling the points on it. You typically also want your connections to lie on the medial axis, right? Because you also want that to be, and that's, it turns out it's possible to kind of do local planning. If you start off with a point on the medial axis, you can kind of stick to the medial axis as you're moving to the next point. And it's also, these things actually work a lot, I won't say better, but it's simpler in RRT-based methods.
Selectively, in order to make it manageable, how do you know that you haven't missed the important points?
Well, you don't, right? You may be happy, if you're happy with your solution, if it's good enough for you, then be happy with it, right? Yeah, well, that's kind of getting to some of the problems we face with the protein application. But, which I'll actually do, I'll skip over the next one, but let me just show you something kind of.
I think it's sort of hitting on this question of sample complexity, right? That sample completeness, right? That you can never say that there's no path, right? That's one of the challenges.
Well, with this toggle method, you can, because you can come up with a disconnection proof. That's one of the other really interesting things for it. But again, only if you really have this like separable property in your space. But yeah, that's one of the challenges, right? But they're working pretty well, right? These are the methods we're all using. So.
Are there any kind of like, is there anything we can say about relating the number of samples we take, the dimension of the space, and the kind of, some bound on suboptimality?
What do you mean by optimality?
The shortness of paths or something.
So, well, there's the dimensionality of the space doesn't often come up into that. This is usually, putting the complexity of your validity check there. But there is work on optimal RRT and optimal PRM star and RRT star. But they, again, are kind of none of these. The problem with pretty much everything we understand about that complexity is it only applies to these uniform sampling scenarios. And those don't usually work, and that's not usually what people are working. So we have kind of theoretical results often that are not about the things that we're using in practice. So there's kind of a divergence in those. So we don't really understand everything yet, but there's a lot that's known, really, and people have looked into these problems a lot. So let me show you something interesting, which I don't really like. So this is this flange problem, 3 versions of it. The 0.85 means we shrunk the tube to be 85% of its original size, 95% of its original size, and its original size. And this is time to solve it. The blue was when we used just our automatic method, this obstacle-based method. And it took, nearly 500 seconds to solve it. What I'm showing here is only the planner time, so we're not counting the time for the user to collect a path. But it just took a few seconds for the user collected a path and it was given to the planner. It took a few seconds for the planner to basically solve that problem using that input trajectory. When we went to the 95% version of the problem, it took about 3,000 seconds for the planner to solve the problem given the input trajectory from the user. Okay? We don't show, the automatic planner would have eventually solved it. I just don't show it here. This one is interesting. Here I took the solution path from the 85% version of the problem and gave it as input to this one. And that one solved it a lot quicker.
So it still had the haptic in the yellow one?
No, I just took the solution path from here, and I gave, so the original one was collected that way, but then I gave it that as the input path here. So it was correct for the 85% version of the problem, but not for the 95% version. And that, the reason for this, I think, is that that path shared some characteristics of, more characteristics of the correct path than that one that the user collected. And in fact, how we solved the problem is we took the solution from this one and gave it as input to that one. So unfortunately, this does not make the case for user, right? Because we could have just started off with an easy version of the problem, asked my planner to solve it, and then iteratively increased it. Anyways, I found that interesting thing. So let's see. Oh, let me at least tell you a little bit. I won't tell you about this. I will tell you I'm working with some colleagues in architecture to use basically just multi-agent simulations to evaluate building designs, and they're interested in evaluating hospitals to see if they'll promote healthy living, both for the nursing staff as well as the patients. If there's light there and if they encourage people to walk more. That's pretty. I was not expecting to have that kind of application. And for the protein folding, I just want to give you a tiny little flavor. So we're not doing, one thing here is to make it clear, we're not doing protein structure prediction. That's what most people think about when they hear about protein folding, is they're given a string of amino acids and they want to predict the native three-dimensional structure of the protein. What we're interested in is the folding process itself. So we assume we already know the native state of the protein, and we want to understand how the protein will go from like an unfolded state to that folded state. And this is important because there's a lot of important diseases which are related to protein misfolding. And so if we could kind of understand that folding process and where things might go wrong, perhaps that can lead to some insight, and they can design therapies. And this is an area where computational techniques are really critical because it's difficult. There are some experimental techniques today where you can get some small movies of proteins folding, but in general, you can't do that at the level which you would need to do to study as many proteins as I'd like. So the way this works is a protein is basically a string of amino acids, and they can basically the angles amongst there can change, and you end up with a three-dimensional structure of the protein. And each one of those has a different, you can compute an energy related to it. And the native structure of the protein is the lowest energy value in general. And you can imagine this whole landscape of all the proteins, of all the conformations. And what we do is we basically use this PRM-based method to map these landscapes. So we do it the same way as we do for robotics applications. Yes?
Is it true that it's always the global?
No, but it's more or less true. In most cases, it's true. It's enough true for most of the proteins that having this kind of funnel concept is used in biochemistry to teach about these things. But we basically come up with all these different conformations, and we calculate their energies. And then we are going to play the same game. For each one, we compute the nearby ones, and we are going to connect them with edges. Here's where we do something that's different than what we talked about so far, is we're interested in particular routes, so we want to know their energetic feasibility. So we are going to give each edge a weight that's related to its energetic feasibility of happening. And the idea is that if it's all downhill in terms of energy, it's going to get a really low weight. And if it goes up, that's going to be unlikely to happen. It'll have a high weight. And then when I'm looking at any one of these, I pull out the shortest weight path from it down to the native state. And that'll be the most energetic feasible trajectory in my roadmap. Not overall, but just the one in my roadmap. And if you're familiar with molecular dynamics or Monte Carlo methods, how this relates to them is those basically will give you a trajectory but it'll be a very fine trajectory, and it'll be pretty accurate. But you can't afford to compute too many of them. And then there's like statistical mechanical models that don't end up with any trajectories at all, but they'll give you some measure maybe about how steep and smooth that folding landscape is. That will give you some idea about how fast the protein will fold. Our method is kind of somewhere in the middle. It can give you many, typically thousands of these trajectories, but none of them are going to be as accurate or as fine-grained as something you get out of molecular dynamics. One of the biggest pains for this kind of work is how you're going to validate it, right? So luckily, some people have come up with, there's a lot of proteins they've studied a lot. There's this protein G. I'll just talk about this one and these two mutants of it. And they were built by David Baker in his lab up at the University of Washington. And basically, he modified these proteins a little bit from this one so that the order in which these two secondary structure portions, which are called hairpins, beta hairpins, form. So in protein G, this one forms before this one, and in new G1 and new G2, the other ones form first. So this is like a really tough case. And what we did is we applied our method to these proteins, and we checked the order in which the secondary structure formation formed on those pathways. And we basically got it right pretty much all the time, 98 to 100% of the time. So this made the biochemists, be interested in our method, and we have like a lot of nice collaborators now. So that's it. Hopefully, if you weren't already convinced, you're convinced that there's like tons of cool problems which we can solve with these methods. All you have to do is apply, define the configuration space, and then how to compute the validity of one configuration, and then you can apply these methods to them. So thank you. And I should also thank all my students and collaborators have done the work. So I'm happy to take any questions.
Going back to your first point on that summary slide, finding the appropriate models and maybe just the C spaces. Is that difficult, and is there an automated way of doing that?
Automated way? Not that I'm aware of, but usually it's pretty natural, right? I mean, for a robot, it's pretty clear. We know what the degrees of freedom are for a robot. You would for a person. All the cases I've shown you, it's pretty natural.
So for the flange case, I can see you probably have 3D position plus some angles, I guess.
Yes.
But if I have a different gadget that maybe has less symmetry, how would you go about defining?
Well, if it's a rigid body, you still have those 6 degrees of freedom, right?
Okay.
If it has some flexibility, you're going to have to model that too. So it's yeah, exactly. But I think it's fairly straightforward.
So also just to maybe repeat something which you said earlier, but is it true that all you really need to use many of these techniques is just a really quick way to check collisions and C spaces?
Yeah, the only things you absolutely have to have is you have to be able to evaluate the validity of a point. I guess that's all you have to. Well, you have to be able to sample a point too. So you need to be able to define a sample and check its validity, because you can do local planning using just that.
So we never need to know anything about the shape of C space. We never need to know anything.
No, I mean if you know things, you can use that perhaps to help you guide your sampling, but you don't need it. I mean they're very elegant methods, and it's amazing what you can do with them. And like even this method that we finally came up with to help us uniformly sample the surfaces, it's the same thing. You're throwing these segments down, and you're just checking, the points at your resolution, which you have also to decide for your problem. You check each one of them for validity.
Okay, folks, I think she has another appointment, right?
Yeah, Alistair, I think, is upstairs.
I think we have to say thank you.
Well, thank you all.